Hi folks, welcome back to the 40S pre-cal videos. In this one we're going to have a look at outcome R12 and we're going to look at the applications of polynomial functions. So there's going to be 4 examples in this video. I'm just going to talk you through it. So I would suggest, if you haven't already tried these questions, read it over, give it a try yourself, and then you could just kind of correct it as I go along. Okay, so here this first example says the volume of air flowing into lungs during one breath can be represented by the polynomial function v of t equals negative 0.041 t cubed plus 0.181 t squared plus 0.202 t, where v is the volume in liters and t is the time in seconds. So the situation is represented by this graph below here. So you can see that we have a graph, and this is the polynomial that is listed up here. That's the graph of it. So we want to look at what the x represents. So the x-axis along here, what does it represent? Well, it represents time in seconds as we breathe in and breathe out. And then the y-axis represents the volume of air in the lungs. All right, so that's going up and down. Then here we want to look at determine whether there's any restrictions on these variables. Well, you know that time can't go negative, right? So we're going to just kind of not look at any of these values here. And also for the y value, we want to look at whether, well, our lung capacity, it can't go into the negative either. So we're just going to cross off all of this part of the graph and here as well. So really we only want to look at the positive x and the positive y. Okay, now next part we're going to use the graph and we're going to answer the following questions. So determine the maximum volume of air inhaled into the lungs. At what time during the breath does this occur? So the maximum, so we're going to be looking for a local max. This is going to be somewhere around here. And we want to read the y value. So that's going to be, the max is going to be the y value, which is at like around 3.3 liters. And the time at which that maximum occurs is 3.3 seconds. So we're just kind of look right here at the max and estimate what that number is going to be. Okay, our next question, how many seconds does it take for it to complete one breath cycle? Now, one breath cycle, that includes the full inhale and exhale. So that's going to be all the way from here to 0. Now, in reality, your lung capacity doesn't really get to 0, but we're just going to look at this model here. So it takes approximately 4.5 seconds. And what percentage of the breath is spent inhaling? So that is when your graph is increasing. So from the 0, and we're going to go up to here, pretty much to where the 3.3 seconds were. So we're going to find the ratio. We're going to write down the ratio of when it is increasing. So we're inhaling for 3.3 seconds out of the 4.5, and that gives us 73% of the time inhaling. Okay, so now let's have a look at example 2. So example 2 is looking at a block of snow, and it measures 3 by 4 by 5, and what's happening is the block of ice is outside and it's getting warm and it's sunny and it's starting to melt. So the initial block of snow is going to be a cube, and then it starts off as 4 by 3 by 5, and then we have a minus x, right? This minus x is representing the length of each side. That's shrinking. So it's shrinking by that much each time. And the polynomial to represent this function is going to be all 3 of those lengths multiplied together, because we know volume is length times width times height. And when we multiply everything through, this is the polynomial that we get. So you want to make sure you multiply these 2 first brackets together and then multiply the result of that with the third bracket. All right, now determine algebraically the dimensions of the new block. Well, that is when the block has a volume of 24 meters cubed. We were given that in the question. What we're going to do is set the left side of the equation to 24, and then the right side is going to be the polynomial that we got in this part right here. And we are going to now solve for x. So we move everything over to one side, set it equal to 0, solve for x. So we're going to use the factor theorem, we're going to divide, we're going to do everything that we've done in the earlier sections of this chapter. And we're going to get the result that the dimensions of the block is 4 by 3 by 2. Because when we got x equals 1, that's the amount that it shrank. And you can verify that the volume of this is 24 meters cubed, since this 4 by 3 by 2 is equal to 24. All right. Now, our third example. So the third example here is referring to a length of a swimming pool. So here we've got the length of the swimming pool. And the length is 10 meters larger than the depth. The width of the pool is 3 meters larger than the depth. So everything is being compared to depth. It also tells us that water costs $2 per meters cubed to fill the pool, and the bill to fill the pool was $240. So we can use this information here to figure out how many meters cubed were actually filled into the pool. All right. So we're going to represent the situation algebraically in terms of the pool's depth. So D is depth, D plus 10 is the length, and D plus 3 is the width. So everything is in terms of depth, and then this is our polynomial that represents the volume. Multiply everything through, that's what we end up with. So we're going to determine all possible values for the depth of this pool, which means that we need to now solve for D. So do everything that we've been doing before, and we're going to solve for D. Using that $2 per meters cubed and the fact that the pool costs $240, we're going to use that to figure out that we actually filled the pool with 120 meters cubed of water. Okay, so there's the work here. And then we're going to multiply this through, move the 120 over, have one side equal to 0. And now we're going to solve for D. You factor this, you use a quadratic formula. There are no real solutions to this quadratic right here. So the only real solution is that D equals 2, and the depth of the pool is 2 meters. And then the dimensions of the pool are 2 for the depth, 12 for the length, and 5 for the width. And then the dimensions are 2 by 12 by 5, and you can verify that the volume of it is 120 meters cubed, which also works because that's what we found here. So it's just another way to make sure that you're correct. All right, now this example is of a box, and you're going to assemble a box by cutting the corners of a piece of paper and then folding up the remaining sides. A piece of cardboard has a length of 30 by 20. Now we're going to cut squares out. So it's like, let's say we take this piece of paper and then we're going to cut squares out of each corner. Okay. And from here, I'm going to cut that out. And I don't know what the lengths are that I'm cutting it out of. So we need to figure out what those values of X are going to be so that I can make my box. All right. Here, it asks to write an algebraic expression that represents the volume. Now see, if this originally starts as 30, I cut an X out here and I cut an X out here. That's where my 30 minus 2X comes from. And same goes on the side here. So I have 20 that I start with, and then I cut an x out here and an x out here, and then I end up with 20 minus 2x. So all I need to do is figure out what x is. So all this work over here is to find what x is. So we have our polynomial with those two dimensions, and then x is the depth. So we multiply these three factors together, and this is the volume of the box that we get. The volume is going to depend on how much you cut that corner out. All right, now here's our polynomial. Starts off with 1,000, so we want a box of 1,000 cubic centimeters. Set it equal to our polynomial here. Solve for x, same idea. We're going to use the quadratic formula for this part, and we end up getting these two values for x here, and we also get a value of x equals 5. Now, so we have three values that are possible. We want to check all of these three in our polynomial to determine the solutions that are valid. And we have to make sure that we eliminate anything that is not a legitimate solution, anything that's like a negative dimension. So if I take these values and plug it in, you can see here for the first one, it works. I get numbers that actually give me a positive volume. This one here, you end up getting a negative value for one of the dimensions. So we need to reject this. So kind of go back up here and say, kind of cross it out so it doesn't, so it shows that it isn't a valid solution. And then over here for x equals 2.93, we see that these work and are legit. Now, in your final statement, you can say that x equals 5 and x equals 2.93 are possible solutions. And I want to restate this. Make sure that you are obvious about rejecting your x equals 17.93 by crossing it out. So just like I did here. All right, so that's your 4 examples. Hope you have some success with these questions here, and we'll talk about this one a little more in class, I think.